Welcome to qnawire.
So firstly, for this problem, let's draw a diagram for the initial position of the assembly and the final position. So at the initial position, we have that the mass center of the rod at point G obviously lies at the center, which is 400 millimeters from either end, from end A and end B. The mass center moves with linear velocity v bar 1, and the distance between G and C is 40 millimeters. Between A and C is 440 millimeters. Between C and B is 360 millimeters. The assembly moves with angular velocity omega 1. In the final position, the mass center is still at the center at 400 millimeters and moves with linear velocity v bar 2. The distance between G and C is 280 millimeters. A and C is 680 millimeters, and between C and NB is 120 millimeters. In this configuration, the assembly moves with angular velocity omega 2. So the first thing we'll do is find the linear speed of the mass center v1 in the initial position. And this is the distance from C of the mass center, 0.04 meters, times omega 1, the initial angular speed. And so this is equal to 0.04 meters multiplied by the angular speed of 40 radians per second. And this is equal to 1.6 meters per second. For the final position, the linear speed of the mass center is equal to 0.28 meters, which is 280 millimeters, multiplied by omega 2. Omega 2 is the speed, the angular velocity we wish to calculate. So the final angular velocity of the system. So what we will do next is we'll apply the conservation of angular momentum about point C. So if we look at our diagram for the conservation of angular momentum about C, we initially have this position, and we have the mass center G, which has a linear momentum m v bar 1. The cylinder has angular momentum I bar dE times omega 1, and the rod has angular momentum I bar AB omega bar 1. The distance between the mass center and point C is 0.04 meters. The final position, the mass center of the rod has linear momentum m v bar 2. The cylinder has angular momentum I bar dE omega 2, and the rod has angular momentum I bar AB omega 2. The distance between G and C is 0.28 meters. So from here, we can take moments about C, but we'll first find the moment of inertia of AB, or the center of AB, and this is 112 multiplied by the mass, which is 3 kgs, and multiplied by 0.8 meters, the length of the rod, squared. And so the moment of inertia of AB, or the moment of inertia of the rod, is 0.16 kg meter squared. Now we will take anti-clockwise moments about C. So we know that the momentum is conserved in the two positions, initially and finally. We will take the anti-clockwise moments about C, and we get that I bar, the center mass moment of inertia for the rod AB, times omega 1 plus m v bar 1, the linear momentum of the center of the rod in the first position, and 0.04 meters plus IDE, the moment of inertia of the cylinder, multiplied by angular momentum omega-1, since the entire system is rotating with the same angular frequency, is equal to the moments about C in the second position. That's I bar AB times omega-2 plus m v bar 2 into 0.028 meters plus the moment of inertia of the cylinder IDE times omega-2. And so we can substitute many values into this and we'll see what we get. So this is, we'll suppress the units just for now. So 0.16, that's kg meter squared for IAB, times omega-1, which is 40 radians per second, plus the mass of the rod, which is 3 kg, into its linear velocity in the first position, which is 1.6 meters per second. We calculated this above, times 0.04 meters plus IDE, which is given as 0.025 kg meter squared, times omega-1, which is 40, is equal to IAB again, which is 0.16 times omega-2, which is unknown, and we wish to calculate, plus the mass of the rod, 3 kgs, into 0.28 omega-2 into 0.28. So this is actually 0.28 meters. So this is 0.28 omega-2, which is V2, into 0.28 plus the final term, which is 0.025 IDE times omega-2. Again, omega-2 is unknown. So although this is a very long equation, it isn't complicated. We have one equation with one unknown. And so if we simplify this equation and we solve for the unknown, we get omega-2 as required. So we actually get 0.4202 omega-2 is equal to 7.592. And hence, the angular speed in the second position, when the cylinder hits the end of the rod at point B, is equal to 18.068 radians per second. So the whole assembly is rotating with angular frequency 18.068 radians per second. And so therefore, we have the angular velocity omega-2 is equal to 18.07 radians per second, and with its given direction relative to C.